Hello, welcome back. There's one handout today, handout number 12, next set of lecture notes. Homework number 2 is due today. You can pile them up here, or bring them right after class to my office. The first programming assignment is due next Tuesday. I assume you're all making good progress on that. Any problems or questions or issues? Okay, last time we completed a sort of once-over-lightly tour through some real-life computer instruction set architectures, and I just want to conclude that with a couple of remarks, I guess, on philosophy or instruction set design. You remember that I mentioned that back in the... Yeah, question?
Yeah, before you get on to the real stuff,
right.
I was just wondering when homework 3 is going to be assigned, not that I want it.
Not that you want it? Actually, it was supposed to have been assigned today. The problem is that it didn't get through the SITN reproduction facilities in time, so we're going to assign it next Tuesday. It'll be a handout next time. I'm sure you're all disappointed that that's going to have to shift. You remember that I said that back in the early days of the 50s and 60s when computers were designed, every new computer had its own instruction set architecture, and designers felt free to design into their instruction set whatever they liked for that particular implementation, which of course meant new compilers, new handwritten code for things, programs, applications written in assembly language, which most things were. So bringing out a new machine with a new instruction set architecture was a big deal. In the mid to late 60s and throughout the 70s, that style changed, and people tended to make a clean separation between the design of the instruction set and the implementation of any particular machine that executed that instruction set. And the classic example of a machine where the separation between architecture and implementation was extremely clean was the IBM 360 series, started in 63 or 64, and still living on today is the 370, 390 series machine. The problem with that is that because you're designing an instruction set architecture for a wide range of implementations in terms of performance, from low-performance machines to high-performance machines, you're constrained, and it makes it very difficult to implement high-performance machines. The pendulum now meaning since the mid-80s and into the 90s, has swung back in the other direction, that as new implementations, in particular high-speed implementations, are created, the designers feel free to reinvent or at least modify instruction set architectures. An example of that is the kind of thing we talked at last time. Remember, the MIPS load instruction was originally specified so that there was one load instruction delay. The instruction following the load from memory was not allowed to use the register that was being loaded because it wasn't ready yet. And if you did, you might get unpredictable results. Well, sometimes you could schedule a useful instruction in that slot after the load, and sometimes you couldn't. And if you couldn't, you had to stick a no-op in there. Well, that's a property of the particular implementation, not a property of the instruction set in the abstract. And in fact, future implementations of that instruction set might require more load delays. Maybe you have to fill 2 instruction slots instead of just 1, or fewer. Maybe the machine can be made faster so that, in fact, you don't need to delay using the loaded register. You could use it right away. And in fact, in the MIPS architecture, those kinds of changes have been made. And in processors beginning with the R6000 and then on the R4000, you're no longer required to stick a no-op into the load delay slot, because if the processor doesn't have the data, it will automatically stall. And if it does have the data, you get the advantage of extra performance by not having to stick that no-op in there. Well, that's okay, and you could argue that in these days when everybody writes in C and C++ and the compiler can handle those issues, that's not a problem. But in fact, it is a problem. And if you ever work in a software company that has to distribute programs that have been compiled for a specific operating system or processor, you realize that it becomes quite a nightmare having to produce versions of your software which not only depend on the flavor of Unix that your customer happens to be running, but the flavor of the RISC processor that he happens to be running. It's just not MIPS versus SPARC versus PowerPC. It's now MIPS 4000 versus MIPS 6000 versus MIPS 2000. So binary compatibility has disappeared. Someday it may reappear again, but it is an issue which where you make different trade-offs depending on how much you value the last bit of performance. And for the last several years, and probably for the next half decade at least, valuing extreme performances gets high marks, and the result is that the distinction between architecture and implementation gets blurred. What I'd like to do now, before we move on to pipelining, is just to briefly go over some instruction set measurements that give us some insight into the way these different instruction set architectures actually perform. And the first thing we can do is look at some instruction count ratios that just show for different architectures and a collection of benchmarks what the ratio of number of instructions executed on each of these architectures is, and see whether we come up with any surprises or we understand what's going on. These benchmarks are sort of a typical academic set of benchmarks, which tend not to include any commercial applications or real-time applications or communications applications. This is a compiler, this is a CAD simulator, and these are both floating point kinds of programs. So one problem in doing any real study like this is to make sure that you choose the set of benchmarks which is appropriate for your ultimate customer base, because those are the people you're trying to keep happy. But given that caveat, what do we see? Well, most of the numbers look reasonable based on our expectations. Certainly, we expect the DLX compared to the VAX to have to execute a lot more instructions because the instructions are more primitive. So in fact, we see that 68% more instructions on the DLX than the VAX for espresso. Comparing the x86 to the VAX, one would expect it not quite to be as bad. The x86 has more and more complex instructions, has more addressing modes, and we expect more instructions than the VAX, but not as many more. And in fact, that's what we see. So this roughly confirms our intuition. There are always surprises, though, and the surprise here is what's happening in NASA 7, one of these floating point programs, where the DLX to x86 ratio is way down, indicating that either the DLX is doing a surprisingly few number of instructions or the x86 is doing way too many. And if you look at this ratio, x86 to VAX, you see that it is also way up. So the conclusion is that something's going wrong with the x86. For some reason on this benchmark, the x86 is executing a lot more instructions than one would expect by looking at the architecture. And in fact, that's true, and I don't know exactly why that is, although in a couple of minutes I'll speculate as to why that is. Well, one of the things we can presume is that a great deal, or much of the difference between the instruction counts on these machines has to do with the availability of addressing modes. So we can start to look in a little more detail at addressing modes and how they're used. This was the chart that you didn't have last time that I showed, that shows which addressing modes are used most often. And we can see that the non-memory addressing modes, register and immediate, are the most common. And after that, of the memory addressing modes, displacement and register indirect are the ones that account for most of the operations. Well, all of the processors have these addressing modes. So what is the penalty for a DLX-like processor to simulate the addressing modes that it doesn't have? Well, with a little bit more statistical information, we have the tools necessary to actually compute what that penalty is. So let's do that as an example. First thing we need to do is to look at the code that DLX would have to generate in order to simulate those addressing modes. So let's look at a typical example. For the 5 most popular memory addressing modes that the DLX doesn't natively have. This kind of translation, by the way, is not just an academic exercise. DEC, in making a transition from the VAX to a RISC-like processor, to the Alpha, I think provides some software that automatically does this conversion to allow their customers to run old programs that take advantage of the VAX addressing modes that don't exist. So let's just go through a couple of examples. VAX allows you to add to a register a memory location pointed to by register 2. Well, DLX is a load store architecture, so you can't do an add and a load from memory in the same instruction. So it takes 2. You load into a temporary register the memory location pointed to by R2, and then you do a 3-operand add instruction that uses the result of that load. So the penalty for DLX not having that addressing mode for the add instruction is 1 instruction. Similarly for displacement mode, although it is recorded as a separate addressing mode for the VAX, in fact for DLX it's the same mode. The displacement can be 0 or a non-zero number. Again, the penalty is 1 instruction. Now we're making certain assumptions here about the fact that the displacement fits in the 16-bit field available in DLX, whereas in fact in the VAX displacement can be much larger and the instruction set, as we saw, is more complex. So there are certain simplifications here which in real life turn out to be reasonable. Auto increment, register indirect but incrementing the register afterwards. Well, same 2 instructions we had before, only now after using the pointer to reference memory we need to increment. So the total penalty for DLX is 2. Displacement deferred, also a total penalty of 2. Load first the word referenced by the displacement addressing mode, then load the word pointed to by that word, that's the indirect operation, and then we can do the 3-register add as before. Again, a +2 instruction penalty. The last and most complicated one is the scaled mode, which takes a register and multiplies it by a constant, adds it to another register and a displacement. Well, the first thing we need to do is to multiply that register by the constant, and assuming that the constant, as it is in most scaled modes, is the power of 2, we can turn that just into a shift instruction, which is typically a 1-cycle instruction on most machines. So we shift the contents of register 3 left by the log of the size of the operand. If you're fetching 4-byte words, you shift this left 2 bits to multiply by 4. Then we can add the 2 registers together. Then we can fetch the operand from main memory using the displacement and the result of the added registers. And then we can finally do the ALU operation. So the total penalty there for not having that addressing mode is 3. So now that we know the penalty for each individual addressing mode, all we need to do is to combine that with the statistics we saw for how often each one is used, and we can estimate what the VAX advantage is, or the DLX penalty is, for its addressing scheme. The only other piece of information we need to know is how many operands there are per instruction, because that penalty will apply separately for each operand of each instruction. And in fact, it turns out that for the VAX, there are about 1.8 operands per instruction, either memory reference or not. So we just go through a standard kind of inner product, or weighted average. We know that 5.4% of the operands cause a 1 instruction penalty for DLX, 20% of the operands are displacement, and they cause a 1 instruction penalty for DLX, and so forth. So the way to calculate the number of additional DLX instructions is the number of additional instructions required for each operand times the number of operands per instruction. And this is just the product of those percentages times the penalty times the number of operands. So 0.371 is the number of extra instructions per operand, and 1.8 is the number of operands per instruction. So the total penalty is 0.66. So that our prediction for this particular benchmark, which is GCC, is that the ratio of DLX to VAX instructions should be 1.66 to 1. So that number is consistent with the ones we saw in that other chart. For some reason, that particular value wasn't filled in on the chart, and it would be nice to know whether our prediction in fact matches reality. Now, this is only one reason why those instruction counts might be different, so obviously this is a gross simplification. Last thing I want to look at in terms of statistical measurements of machines is to look a little more in detail of those instruction counts and what kinds of instructions vary from machine to machine. First thing to point out is that this comes from the book, but the book has a bug. It's column doesn't add to 100%, and I believe that the error is that this value, the SPICE DLX measurement for logical instructions, should be 15% and not 5%. The other thing to notice is that there's no such thing as a typical program, that numbers across the benchmarks, even on the same processor, vary a lot. Control instructions on the x86 will vary from 23% to 4%. So it really makes it important to choose an appropriate mix of benchmarks in order to be able to adequately characterize the machine. The big surprise here, again, is on NASA 7, and the numbers which are amazing are the counts of instructions on the x86 for data transfer and integer arithmetic compared to, say, DLX. In most of the other benchmarks, the numbers are comparable, and in the NASA 7 benchmarks, the numbers are off the wall. And in fact, for this benchmark, the x86 executes about 2 or 2.5 times as many instructions as DLX does, despite the fact that they have more complex instructions in general. I don't precisely know the reason for this, but I have a guess. But before I give my guess, does anyone else want to have a guess? Why is it that it might be so bad for the x86 on this application? Yeah?
Well, there's a lot more floating point in the DLX showing up there, so that seems to be taking some slack up from somewhere.
That's true, and one of the things you might look at is the number of floating point operations DLX compared to x86. It's much higher on the DLX, and part of the reason for that is that the x86 has transcendental functions built in. Remember, these are instruction counts, so their counts are way down for floating point compared to the DLX, because the DLX has to simulate floating point operations.
Well, they actually have about the same number of floating point because you have to triple the x86. But I think there's the main difference is there's a lot of data transfer, and I think the reason behind that is something like your loop variable doesn't have room in registers, so it's going out to memory every single time to do indexing, things like that.
Yeah, I think that's one very good explanation, in fact, that the x86 just has fewer registers, so there's some tight inner loop in this NASA code that is being penalized for having to load and store temporary results into memory, where DLX with enough registers doesn't have to do that. I suspect there's something else going on, and if you remember last time I said that in the 286 version of the x86, there's this complication about what pointers are, that pointers can either be short pointers or near pointers that have only offsets, or far pointers which have not only an offset but also a segment part, and you need to use far pointers when you're accessing data which is bigger than 64K. It in fact can get even worse than that. If you're accessing any single piece of data which is bigger than 64K, then pointers become so-called huge pointers, where you have to, for each individual array, have to manipulate both the segment part and the offset part. The code that the compiler generates for far or huge pointers is absolutely horrendous. It makes one shudder to look at it. And my suspicion is that this benchmark for the x86 was done in 286 short offset mode and not in 386 long offset mode. And it's manipulating somewhere in the very important inner loop of that program far or huge pointers, and causing a lot of segment manipulation and a lot of register manipulation just to do the addressing right. If that's true, and if this x86 benchmark would be repeated in 386 long offset mode, I suspect these numbers would be very different. But that's just my speculation. Last few remarks about instruction set architectures before we move on to a different topic, pipelining, which is a kind of summary of where different instruction set architectures came from. Back in the early days, if you had very limited hardware and very primitive compilers, then under those circumstances it might be reasonable to come up with a stack architecture. If you have a lot of high-level language support and memory cost is high, and because memory cost is high, you want few instructions. You want your program to take as little space as possible and to need to be fetched from memory as infrequently as possible. Then that leads to an orthogonal CISC-like architecture, kind of VAX architecture where instructions do a lot and it's easy for the compiler to compile to them because you can do any kind of addressing mode, say, on any kind of opcode. So this leads to a VAX-like machine. If you have a limited amount of hardware, like the first microprocessors did, where they had to be able to fit everything on a single small IC, and you expect that a lot of the programming is going to be done not by compilers but by hackers writing assembly code, then you're led to a register set design that has a small number of registers. Small number of registers take small amount of space on the IC. They're easy for people to deal with, and this is how the original 8086 style of computer was developed. If in fact you're more interested in efficient pipelining and you have optimizing compilers, not people doing the assembly language programming, and those compilers can do a lot of instruction reordering to keep the pipeline running efficiently, and in fact you have good caches, so keeping the program extremely small is not so much an issue anymore, then you're led to design machines that look like the current hot topic, which are the RISC architectures. So the desirable features of an instruction set will vary a lot from generation to generation, depending on the implementations that are available and the technology people are using, depending on the compilers and the technology that compilers currently have in them, and depending on ancient history and how much compatibility with prior machines or programs you have to maintain. So what's happening in the future? Where are instruction set designs going? Well, nobody knows for sure, but there are a couple of clear issues. One is that in the interest of getting things to run even more faster, it's important to be able to get even more instructions to execute in parallel. Pipelining, which we'll talk about in detail, will be one way to get that to happen, but there may be other ways in the instruction set, like, for example, having more registers to allow more instructions to be executing in parallel. Sometimes, for example, more registers might be part of the architecture, things that the programmer actually gets to use, and sometimes they might actually be hidden real registers that are really not part of the instruction set architecture, but are there for the implementation to be able to more efficiently use the registers that the programmer specifies. And in fact, we'll see some of that later on. RISCs started out as pristine and pure and really simple, and they've been getting ever more complicated, and one would expect to see that trend within reason to continue. One expects even tighter integration between the compiler and the instruction set architecture. I think this issue of allowing the instruction set architecture and the implementation of that instruction set to affect each other hasn't yet reached its local maximum at the moment, and in the next few years I'm sure there will be even more of that kind of integration. And the kind of thing I was talking about last time, where the compiler or even the programmer could generate hints to give the implementation, give the processor a better idea of how it might optimize the execution of particular instructions. Branches and memory accesses are two examples where that can happen and be productive. Another technique which people are talking about more and more is even a further step in the direction of mixing the architecture and the implementation, and it's the so-called very long instruction word processor. Rather than having a 32-bit word that specifies one operation and leaving it to the processor to figure out how multiple streams of those can be executed in parallel, you could in fact think about assembling a whole bunch of operations in parallel into one very wide word, like 128 bits wide. And in that case, the compiler does the multiple issue scheduling. The compiler figures out what things can be done in parallel in a single one of those words. Those kinds of machines can be made to run extremely quickly, but then the compiler has to know a lot about the internal implementation design of the machine, because it has to know what things can be done in parallel and what things can't. But there will be a bunch of machines that you see designed like that, and if we have time, we'll talk about some of them later on.
Question?
Yes.
Have there been studies done to determine whether or not the benefit you get from VLIW is actually in the hardware, or whether it's just the compiler optimization?
I'm not
sort of giving the compiler knowledge of what's best for the processor, if you're going to be doing multiple issue anyway.
I guess I don't know whether good studies have been done. It becomes very complicated to determine what effect what part of an effect can be attributed to a compiler and what part of an effect can be attributed to an implementation. Because those two things are so tightly integrated these days, it's very hard to make a clean study saying, you know, change the compiler to do multiple issue scheduling, but don't do a very long instruction word implementation. The answer is there are people who are even now doing those studies, but they're hard to do cleanly.
Compilers currently do multiple issue scheduling.
Yes.
So I guess, you know, so I don't think that's an issue. I guess it's just how much faster can you make the hardware for not having to figure stuff out. Is that a right assessment?
Compiler can do multiple issue scheduling, but it still depends a lot on the recognition of the processor to be able to know what things can be done in parallel. In a very long instruction word type architecture, the processor basically trusts the compiler to have made those decisions statically at compile time, where you have all the time in the world and not just 10 nanoseconds. And the decisions about what things can be done in parallel are made at compile time rather than execution time. It should be an advantage. We'll talk about that more later. Any other comments before we go on to the topic that I've been referring to off and on throughout, which is pipelining. Pipelining is a technique to make computers go faster, which hasn't been invented just recently. The earliest machines that did pipelining, I guess, commercial machines were probably mid-70s, I think, or early 70s, the 31691, and maybe even machines before that. But it's a technique which is the dominant technique right now for high-performance implementation. The next few lectures will have this kind of an overview. The first thing we're going to do is look at a simple implementation of a RISC processor, this kind of subset of MIPS called DLX, without pipelining. This, for people who have taken 182, will be a very brief review. For people who haven't, I'm sure you will have seen that kind of organization, non-pipelined organizations of machines before. Then we'll talk about pipelining in general, what it is, how one computes, the speed up that pipelining can give you, some of the nasty realities of how you do reliable clocking in pipelining to get all of the data moving correctly. And then we'll go back to DLX and overlay the machine design we saw before with a basic pipeline and see how it works. And then we'll talk about more nasty realities, and this time at a higher level of DLX pipelining, to realize that the simplified approach to how pipelining works doesn't really work in reality, and there are lots of complications that we have to solve before you can actually build a pipelined RISC machine and sell it to your customers. So that's the outline. First thing to do is to briefly review the DLX instruction format. We went over this last time, so I won't spend much time on it, but it's convenient to see on a single page how the three instruction types lay out. Notice the thing that we were talking about last time, for example, that the register specifier for destination register might appear in one of two different places in instructions, depending on whether it's an R-type or an I-type instruction. But these are the only three formats that we need to worry about. The other thing I might point out is that bit numbering within a word for instructions is another one of these issues like little endian versus big endian, which basically doesn't matter, and unfortunately people have done in different ways. About half the current RISC processors number bits this way, half the current RISC processors number them from 0 to 31 in that direction. The book, in fact, is inconsistent. I found places where it does one and other places where it does the other. I've tried to be consistent in numbering bits most significant to least significant like this. If there are any leftover remnants from the way I did it the first time, I'm sure you'll point them out. Unlike little endian versus big endian, by the way, notice that this bit numbering convention is purely theoretical. If you change the bit numbering convention, it doesn't change anything about the implementation of the machine. It doesn't change anything about whether programs run or don't run. The only thing it changes is the manuals that describe the instruction set and lecture notes like these. Now that is because there are no instructions that reference particular bit numbers. In other instruction set architectures, that's not true. And instructions on the VAX, for example, that allow you to extract individual bit fields by numbering the beginning and ending bits of those fields, the numbering of the bits affects the encoding of the instructions. Or if you have an instruction like, tell me what the first 1 bit is in the register and return to me the number of that bit, that would be affected by the bit numbering. But I think nothing that we do or in most RISC machines has that complication. Okay, here is a DLX implementation. And I claim that this is reasonably complete. Let's walk through it real quickly. Obviously, we need an instruction memory to store our 32-bit wide instructions. We need a program counter to be able to address the memory. So the instruction at the address specified by that program counter is read out into an instruction register, which is 32 bits wide and gets split up into multiple fields. In preparation for the next instruction, we need to increment the program counter by 4. This is an adder that does that. Static adder that just adds 4 to the PC, produces PC plus 4. PC plus 4 will eventually have to get stored back into the program counter in order to fetch the next instruction. Sometimes, however, when we do a branch or a jump, we're going to have to choose a different PC, one that we will compute based on the jump and branch addressing modes that we saw, and choose that one instead. So this multiplexer basically chooses whether to store PC plus 4 into the PC or the computed value coming out of the ALU. If I go too fast or anything is confusing, let me know. I'm assuming that all of this is old hat to you. There is a register file which contains our 32-bit registers. And in fact, I've designed this register file so that we can read 2 registers simultaneously. We read register A based on bits 25 to 21 of the instruction register, and a register B out of bits 20 to 16 of the instruction register. And they come out of A and B ports on the register file. Now notice that one of the nice things about the way the DLX instruction set was designed was that register A and register B specifiers are always in the same place if they're there. So I can always, without any multiplexers or without making any decisions, read those registers out of the register file. It may in fact be that one or both of them shouldn't have been read because I didn't need them, but that doesn't matter. For writing to the register file, life is not quite as simple. In that case, the destination address of the register to be written can come from 1 or 2 places in the instruction. It's either bits 20 to 16 or it's bits 15 to 11. And in fact, there's another case where it's a constant 31 rather than a register specified in the instruction. You remember where that's from? Anyone? Say again? Jump and link, where you have to store the PC plus 4 into register 31. Okay, so moving on along. We've got one ALU here which is going to be used for multiple purposes. In the case of simple register ALU operations, we're just going to choose for these multiplexers to read the register A result, the register B result, and compute the addition or the or the subtraction or the AND of those 2 register operands. The result of that ALU then has to get back into the register file. In that case, it takes this path. It moves around the data memory because we're not using data to or from memory, and then back into the register file. In the case of an immediate instruction, one of the operands comes from the register file. That's the A output. One of the operands is a signed extension of something from the instruction register. So while we're doing all this register fetching, we can also be taking an immediate field from the instruction and sign extending it to 32 bits. So we can add it with the contents of register A and send that back around to the register file. That explains these 2 inputs of this multiplexer. The top multiplexer has to have a second input because of jumps and branches. Sometimes we want to take the current value of PC plus 4, add it to a register or to an immediate, and produce a new effective address for the next instruction. We use the same ALU to do that. Feed PC plus 4 into the top half, feed either a register or a sign extended immediate field into the bottom half, produce the updated PC and choose that instead of PC plus 4 to write back into the program counter. The only thing I haven't talked about is data memory. The address from the data memory comes from the ALU because we need to do the effective address calculation. We need to add the displacement, which is a sign expended immediate field, to the contents of a register to produce the address of the data to reference. The data input, in the case of the store, comes from the other register. The data output, in the case of a load, goes back to the register file. So in fact, I claim that that is a complete implementation of the DLX instruction set. And in fact, this shows all of the so-called thick wire paths, all of the data paths, and that the only thing that's missing in this diagram is the thin wire controls, the controls that specify which direction these muxes should go at any given time. You all believe me, by the way? Is that true? Okay. Now, the other thing to look at, and well, let's do it in this order. The next slide shows the details of all of the operations that occur at each stage, and I divided them into groups based on which things happen for all instructions and which things don't. So for all instructions, we fetch the instruction, we increment the next PC to be PC plus 4, we fetch the two registers. The ALU operation, which is this row here, basically depends on the instruction type it is. You're either adding two registers, or adding a register to an immediate, or adding a register to an immediate for a load and store effective address calculation, and so forth. Now, one of the things to note is that all of these operations, except the ones that are shaded, are combinatorial operations. They don't require any clocks. They're just logic that flows through. And in fact, that entire diagram that I showed you is basically one big combinatorial logic block. You can just fetch the instruction and let all of the results sort of filter through the logic until you're ready to do something for the next instruction. And those doing somethings are the things that are shown shaded here. In the case of a store instruction, it's clocking the data memory so that it gets its results stored. In the case of a register write, something that returns the result back to a register, it's clocking the register file so that its result gets written. And in the case of all other instructions, in addition to those things, it's updating the PC, either from the next PC or from the output of the jump or the branch. So in fact, this could be a one-cycle implementation of the DLX instruction set that simply clocks out the current instruction, waits until all of the propagation through register files and ALUs have finished, and then issue a clock that puts the results into registers, memory, and the next PC. Any questions about
what exactly do you mean by combinatorial?
What do I mean by combinatorial? I mean combinatorial logic is a logic is simply ands and ors, basically. It's logic where the output is a simple function of input, and there are no clocks. There are no timing signals that are part of that combinational logic, and there's no storage as part of that combinational logic. It's just a function of the input that produces an output with no value stored and no clocks to indicate when things should happen. It's just sort of a bowl of spaghetti, and you drop things in the top and eventually drips out the bottom. And the whole machine can be built like that, except for those times where you have to store something that lasts for a long time, like things you store in memory, registers, or the program counter.
But realistically, the data equals the one for load, I guess a third row for loads.
Yeah.
Shouldn't that be shaded also, or?
No. Not in the same way that reading the instruction memory is not shaded and reading registers as memory is not shaded. My model here for the data memory is that it's a combinatorial logic block. It's a block where you feed it and dress in the top into this bowl of spaghetti, and sometime later the data result drops out the bottom. Now, in fact, for at least complicated memory systems, that it's not that simple. And in most memory systems, there is clocking, and it may in fact be a multi-stage memory system that has a cache and virtual memory and other stages. So this is a simplified view of how main memories work. It's not so much a simplified view of how registers work, and registers are just memory after all. The view is that as soon as you change the address coming into that register or memory, a little while later you'll get new data coming out the bottom of it. So it's that model of memory reads that I'm trying to use. For memory writes, you can't quite be that simplistic, because there's got to be a signal that says the data has been stable for long enough, the address has been stable for long enough, now's the time to remember that information. Yeah?
What I was saying is the address could be invalid.
Sure. In fact, for all of this combinational logic, as soon as the input changes, the output may be invalid for a while. And it'll take a while for this bowl of spaghetti to produce stable results after the inputs have changed. But that's just a function of the way combinatorial logic works. You change its inputs, sometime later you may get part of the results, eventually later you get all the results.
What I'm saying is if the address is an invalid address, let's say that doesn't exist in physical memory, you try to access it.
Ah, okay.
Because it's different from the registers, because all the registers are valid.
Right. That's another complication of real main memory systems that we have to deal with. The address may be invalid if you can have more addresses than data. If it's a cache, it might not be in the cache, and you might have to wait a while for the data to come back. If it's a virtual memory translation, it might not be in main memory, but it might be out on the disk, and you have to interrupt the processor. You're right. There are a lot of nasty realities which I'm choosing to avoid for the time being. Any other questions? Okay, that's DLX. Let's look at what pipelining is and how we might apply it to a DLX machine. Notice that although I described that machine as a single cycle machine where you feed all the results in at the top and something happens at the end, you can consider breaking that operation up into multiple steps and break it up any way you like. You know, one step might be fetching the instruction out of the instruction memory. Another step might be fetching the registers out of register memory. Another step might be doing the ALU operation. Another step might be writing registers back to the register file. Whatever sequence of instructions, of steps you want to consider an instruction to have taken, that sequence has to be done for each instruction in sequence. Once you're done with instruction number 1, you do that same sequence for instruction number 2, you do that same sequence for instruction number 3. And this particular picture shows each instruction, this is one instruction here, divided into 3 steps. So it takes 3 cycles in this model for each instruction to get out, and the number of instructions you get out is 1 every 3 cycles. The big breakthrough in pipelining was the recognition that you don't have to do that. In fact, you can start instruction number 1 executing step number 1. When instruction number 1 gets to step number 2, you can start the next instruction doing step number 1. When instruction number 1 gets to step number 3, the next instruction can be doing step 2, and you can start a third instruction, step number 1. At any particular time, this is time I, you've got an instruction executing in step 3, another instruction executing in step 2, and another executing in step 1. What happens? Well, it still takes 3 cycles for an instruction to start, get through all of its cycles, and finish. So the latency for any particular instruction is exactly what it was before. The advantage is that the throughput isn't. The throughput now has increased by a factor of 3. Rather than getting 1 instruction finished every 3 cycles, we get 1 instruction finished every cycle. Now, one of the things that makes this work is that if you look at any particular point in time, each instruction that you're partially executing is in a different phase. And that depends on the fact that we've got each instruction using each of these 3 phases only once. If, for example, instructions used one of the phases twice, like if we had an instruction sequence that used phase 1, phase 2, phase 2, and phase 3, we'd have a real problem. Because the next instruction that was going to issue would do its phase 1 when instruction number 1 was doing phase 2, but it would be trying to do phase 2 at the same time that instruction 1 was doing phase 2. And there we have a conflict. This is only one example of many restrictions on the kind of cycles that pipeline machines can support, and restrictions on the throughput that pipeline machines can attain. And we'll go into that in lots of great detail. Let's look at what this pipelining means by looking at a simple 3-step pipeline for some processor. As before, we have instruction memory. Now remember, before we had all of this combinatorial logic, and after you fetching the instructions, the data just flowed through the combinatorial logic, and when it was done, when enough time had elapsed for all of the changes to be made, we clocked the results back into registers, these results, back into registers, back into memory, and back into the PC. What we're doing now, because we're dividing this execution into 3 separate phases, is to provide additional latches for us to hold intermediate results. So we've divided the combinatorial logic, which was before 1 bowl of spaghetti, into 3 bowls of spaghetti. The first instruction that we issued is in its last stage of execution, let's say. It's in step 3. So all of the information that it needs to execute is currently latched here, and it's making its way through this final step, waiting for the results to be able to be stored in this final result register. In the meantime, the instruction that's 1 instruction later than it is only up to step 2. All of its information is stored in this latch. Its computation is flowing through this logic, waiting to be at the end of the cycle latched into this latch. And similarly, the first instruction, or the latest instruction, the one that we just most recently fetched out of main memory, is undergoing its first phase and waiting to be stored in this latch. All of these latches and the results are basically clocked at the same time. At each step, you're waiting for 3 different instructions to filter through their combinatorial logic. When that happens, you give 1 clock that says, latch these results, latch this intermediate data, latch this intermediate data, and read out a new instruction from memory. All instructions move in lockstep toward the next phase. Make sense? Okay, so let's compute how much speed up we get for this.
Question?
Yeah.
Going back to where you were saying about how one instruction might have 4 cycles, where you get a conflict.
Yes.
Doesn't the compiler find those errors and can say, okay, well, we'll wait on that one?
No, that's not an error necessarily, and in fact, we try in a simple pipeline like this to design it so that every instruction takes exactly the same number of steps. We'll see later that if you have instructions where some instructions are long and take a lot of steps, like floating point operations, in fact, you may have conflicts for particular resources in the machine. That's not something the compiler can always deal with. Sometimes it can, but often it can't, and the machine itself has to have stuff built into it to delay some instructions relative to other instructions so they don't conflict. We'll see a lot more about that later. Okay, how much does this win for us? Well, you can think of the time per instruction as being composed of 2 parts. One is the number of cycles that instruction takes, and the other is the amount of time for each cycle. And you can think of pipelining as either reducing the cycles per instruction. If you start from a 3-cycle non-pipeline machine, then what you've produced is a 1-cycle pipeline machine. Or you can think of it as reducing cycle time. If you start from our original machine, which was a non-segmented 1-cycle instruction, what you've done is reduce a very large cycle time to a very small cycle time. In any case, the overall speed up that you would like to see is that the time per instruction before you pipelined it over the time per instruction with the pipeline should roughly be the number of pipeline stages. And the picture I showed demonstrated that we had 3 pipeline stages, and we were able to get a throughput which was 3 times what we got without the pipeline. Well, there are a couple of problems. One is that requires that all stages be perfectly balanced. It means that every stage takes exactly the same amount of time as the stage before it. You can't have stage 1 taking 5 nanoseconds and stage 2 taking 10 nanoseconds because they're being done in parallel for different instructions. Sometimes it's hard to do that, and we'll see why that's true. The other is that this improvement only works when you can ignore the latches, when you can assume that those latches that you inserted are free. They don't take any additional time. And in fact, that's not the case. The other thing it assumes is related to the question you just asked and my answer, which is that it assumes that you never have to stall, that you can keep this pipeline going in lockstep, one instruction being issued every cycle, and you don't have to make any instructions wait because they conflict with other instructions. Well, that's not true, and you have to add stall cycles. So the ideal speed up that we expect from pipelining is limited by these factors. The ideal number of cycles is limited by the fact that you have to add additional cycles when you stall the pipeline, when you have to delay certain instructions. And the cycle time is limited because it's not only the time of the longest pipe stage, but you also have to add time for the latch overhead. And we'll see how to compute that in a second. Let's first look at an example that shows why assuming identical pipe stages leads to a problem, or how much of a problem it is. Let's assume that we have an unpipelined machine that has a total latency of 42 nanoseconds divided into 3 different parts, a 10 nanosecond part, a 16 nanosecond part, and a 14 nanosecond part. And then the latch overhead at the end for storing results in the register or the memory or the PC is 2 nanoseconds. So the total latency for this pipeline is 42 nanoseconds, and the throughput is 1 instruction every 42 nanoseconds. Now, the reason why these numbers are the way they are is because that's where the natural breakpoints for this particular machine fall. You know, it takes 10 nanoseconds, let's say, to read out an instruction from memory. Then it takes 16 nanoseconds to fetch registers from the register file. You can't arbitrarily move this boundary because it depends on what the functional blocks are in the machine. You can't do 10 nanoseconds of instruction fetch and 3 nanoseconds of register file access and then put a pipeline latch in. You've got to make the pipeline breaks at natural functional unit breaks. So what happens when we pipeline this machine? Well, we've got to design the size of the pipeline cycle for the worst case largest segment, which in our case is 16 nanoseconds. Now, if the pipeline registers also have a 2 nanosecond delay, we've got to add those 2 nanoseconds to every pipeline stage. So our basic pipeline cycle is 18 nanoseconds. The only one that fills that stage completely is the 16 nanosecond cycle, which takes all 16 nanoseconds plus 2 nanoseconds from the latch. And the others have a gap, and that gap is wasted space. This is instruction number 1 that has a medium-sized gap in the first stage and a small-sized gap in the last stage. The result is that the latency is in fact worse than it was for the unpipelined machine. Instead of 42 nanoseconds, it's now 3 times 18 nanoseconds, or 54 nanoseconds. So the time it takes an instruction to get out after having entered the pipeline is longer than it was before. The advantage is that the throughput is higher. We get more instructions per second out, or instructions per nanosecond. And in fact, in this case, we get 1/18th instruction per nanosecond out, which is a speed up not of 3 times that the ideal pipeline would have allowed us, but only 2.3 times. So it's good, but not ideal. By the way, what's happening during this time? This time after the 10 nanoseconds of stage 1 used until the end of that cycle, what's going on? Where are the results for that stage? Okay? Use the speaker.
They're stored in the pipeline latch.
Well, they're sort of stored in the pipeline latch, depending on what you mean. They're actually stored in the combinational logic. If we go back to the simple pipeline, let's say that this stage takes only 10 nanoseconds, and in fact the cycle time is 18 nanoseconds. Well, at the beginning of the cycle, the data is valid at this latch. 10 nanoseconds later, they've made their way through this logic, and they're sitting over here. So in fact, the results are sitting at the input pins of this latch, waiting for the next clock to come along. So they're not really latched in this latch yet. They will be latched in that latch at the end of the cycle. The input to that stage is latched here, but the result computed by that stage is not latched anywhere. It's just sitting on the input pins of this latch, basically flowing through this bowl of spaghetti, this combinational logic. Okay? Let's look in more detail at the other part of why pipelines aren't as fast as we would like them to be in the ideal world. And that has to do with clock overhead. This is a slightly more detailed diagram of what these pipeline registers in between combinational logic cycles might look like. And for this example, I've chosen a particular kind of flip-flop, which are single phase, which means only one clock, edge-triggered flip-flops, which means that the data on this flip-flop is sampled at the rising edge of the clock. So that the clock looks like this. The rising edge is the one at which these flip-flops sample their input data and memorize it, and with some propagation delay later makes it appear on the output pin of that register. The falling edge of the clock is basically irrelevant. Nothing happens at the falling edge of the clock. And the only reason why you need a falling edge is that you can't have rising edges unless sometimes you have falling edges. So these are the kind of easiest flip-flops to deal with. Now, one of the characteristics of flip-flops like these is that the clock rises and memorizes what's on its input pin, the D input, but that data needs to have been there somewhat before the clock rises. And that's referred to as the setup time. And if you look in a manufacturer's spec sheet for 7474D flip-flops, it'll tell you that the setup time is 2 nanoseconds or something like that. So the data has to be there before the clock rises. The output appears on its output pin sometime after the clock has risen. And that's the propagation time through the flip-flop. And that's also quoted in the manufacturer's data sheet as the propagation delay will be never longer than so many nanoseconds. So how do we compute the time between clock signals? Well, we know that the data at the input to one clock stage has to be ready, T-set up before the clock rises. So that's one factor in our computation of the distance between clocks. It's going to take T-prop for the data to get to the output of the flip-flop. So that's another factor we have to add. And then before the clock, remember the clocks are the same on all flip-flops, before the clock at the next stage can rise, we've got to be able to get through all of the combinatorial logic. So that's T-logic. So the period has to be at least bigger than the sum of the delay through our combinatorial logic, the setup time for the flip-flop, and the propagation time through the flip-flop. Now there's another complication. One of the assumptions I made was that the clock gets to all flip-flops at exactly the same time. Well, tain't so. The clock in one flip-flop may vary plus or minus a certain amount around the time when it should arrive, depending on a number of factors. One is wire delay. Depending on how far it is from the source of the clock to the flip-flop, it may take a more or less amount of time. Wire delay is a half a nanosecond or a nanosecond and a half per foot. And although there aren't too many feet in an IC that's a few millimeters square, wire delay is still an issue. The other is buffers. Sometimes you have to, for electrical reasons, buffer the clock for a stronger signal, and those buffers take time. The other is that it's always amusing to watch people draw diagrams of signals that look like this with perfectly vertical edges. In fact, in real life, they're not. In real life, especially high-speed signals look, more like this. They're rounded, and there's a finite amount of time it takes for a signal to get from the 0 state to the 1 state. And the point at which any particular piece of logic recognizes that it's made that transition may vary by a few millivolts up or down, depending on that particular implementation. So that will change when it is that any device recognizes that the clock has risen. So those three components contribute to the fact that all of the flip-flops don't see the clock at exactly the same time. And in fact, if you count T skew as the distance that that clock could really be off from where it should have been, then in worst case, you've got to add to our clock period twice that value. Because in worst case, the clock getting to this flip-flop might be T skew late, and the clock getting to this flip-flop might be T skew early. So you just squeezed the time period you have to do combinatorial logic by 2 times the clock skew.
Question?
Yeah.
So actually, T setup ends when T skew starts, or something like that. I mean, they are like, because the way it's written now, it seems as if T skew is part of this setup.
No, T skew is not part of T setup, and I drew it this way only because I didn't want to show it all on the same edge and confuse the edge. In fact, T setup has to become before the earliest edge, so they go in parallel, in series with each other. Now, in machines that are relatively... Oh, let me not make that comment here. Now, one of the questions is, can we do any better than this? As cycle times get faster and faster, and the overhead, these three components, which together you can consider to be clock overhead, as you increase the amount of pipelining in computers and make the delay through the logic smaller and smaller, the fraction of time that this overhead represents increases, and it gets to be a serious consideration in the performance. One of the questions is, can you do any better than this? I want to go over, just briefly, other ways that clocking is done, in fact, to do better than that. And one way, which is in fact much more popular than those edge-triggered flip-flops, is to use a faster kind of flip-flop called a transparent latch. The property of a transparent latch is that the data isn't sampled only when the clock edge rises, but in fact the data is sampled all during the time that the clock edge is high. Whenever the clock is high, changes on the input to the latch will eventually, after a propagation delay, be reflected on the output of that latch. So in fact now we can somewhat decouple the clock edges from when the data is needed and the output appears. And if we manage to do that, let's say that the data from one stage arrives at the flip-flop while the clock is already high. Well, then we don't have to worry about clock skew because we're away from the edge. All we have to worry about is how long the propagation delay is through that latch from the time the D input arrives to the time the Q output changes. Then we have the delay through the logic. And if that is such that the clock on for the next cycle is high, we don't have to again worry about setup and hold times with respect to the clock edge. So the total period can in fact be as good as the delay through the logic plus the propagation delay. I'm waving my hands a bit here because there is more to this story, but in fact if the system is well designed, you can get this improvement, where the period is a sum of the logic delay and the propagation delay through the flip-flops and not of the hold and setup times. And in fact, most pipeline processors use some form of transparent latching. Now, one of the things that causes this to be a bit of a problem is that now not only is there a delay on how slow our logic can be, but there's also a delay on how fast our logic can be. Consider that if the output from stage 1 changes while the clock is high, and that stage is so fast that the result gets to the next stage while its clock for the same cycle is still high, then in fact you wind up latching the data too soon. You wind up latching a cycle earlier than you should have. So in fact there is now a minimum bound on the logic as well as a maximum bound on the logic. Sometimes you have to wind up, for fast paths, adding arbitrary delays into the middle of the combinatorial logic so they don't appear too early at the inputs to the next stage. Well, there's a way to get around that too. And one way to get around that is in fact not in adjacent pipeline stages to use the same clock. And dual phase clocking is in fact very popular in lots of machines. And it gets around the fast logic hazard, because if it's a dual phase non-overlapping clock, then when this clock input to this stage is high and its output has changed, even if it's infinitely fast, it won't get latched into the next stage because its clock doesn't occur until the first clock is down. And by using this kind of dual phase non-overlapping clocks, you can avoid some hazards. You pay some penalty in performance, and in fact many machines have been designed that allow dual phase clocks but in fact have them overlapping. And the analysis of the required minimum and maximum logic delays for dual phase clocks gets to be a very complicated exercise. And if you're interested, there's a paper that's referenced in the bibliography section of the book that's actually quite interesting, that goes over all three kinds of latches, the D flip-flop latches, the single phase transparent latches, and the dual phase clock latches, and mathematically derives the constraints for the logic delays. One of the more advanced techniques, and this is the last thing I'll say about clocking and advanced pipelining techniques, is that if you are willing to set minimum and maximum delays on the propagation through the logic, one of the things you can think about doing is removing some of these pipeline registers. If it takes a while for data being fed into this bowl of spaghetti to get out to the other end, well, why don't you just wait a while until it's sort of halfway done? And then you can start another bunch of input coming in, and if the delays are well controlled, it won't bump up against the first set of inputs that is making its way through the logic. And in fact, this is done, or at least proposed, and it's called wave pipelining. And it's a way to reduce the clock overhead by reducing the flip-flops that gets clocked. You put two waves of signals through one set of combinatorial logic whose propagation delays are carefully controlled, and you get two pipeline stages for the cost of one. If you're interested in this kind of thing, take the next course, EE282 from Mike Flynn. He talks a lot about this and analyzes it, and he and his group have been doing a lot of the state-of-the-art research in wave pipelining and how much can you get out of it, and how many waves can you really get into a bunch of combinational logic between two flip-flops before they begin to drift apart or drift together and collide with each other. It's a fascinating topic. Any questions on pipelines and clocking and such? Well, given the fact that we now know how to do pipeline implementations in clocks, how do we divide a given implementation into stages? Well, here are the rules. One is that we want the time of each stage to be roughly the same, so that we avoid wasted spaces we saw before. The other is that we need each stage to be used at most once in each instruction, because otherwise two instructions that are in different stages might be trying to use the same stage or the same resource. There can be stages that don't get used in some instructions. If it's not a load store instruction, for example, there might be a stage that accesses main memory, but a particular instruction will choose not to use it. There has to be a place to conveniently hold state information between stages. So trying to break up an ALU, for example, that's adding two 32-bit numbers into two stages so that one instruction can be using the first half and the other instruction can be using the second half is a tough thing to do. Not impossible, but tough. But we've got to be able to define where the registers are that save all of the state information that you need for a particular instruction in a particular stage. And then you don't want too many or too few. You don't want so many stages that the time in the combinatorial logic is extremely short compared to the latch overhead, because then you're dominated by latch overhead. And you don't want so few stages that you don't get the performance benefit that you're hoping to get from pipelining, especially after you consider the fact that you're going to lose some cycles when instructions stall. So this is a bit of an art, and there's no scientific way to do it, but there are guidelines. Let's look back at the stages that I had written for the non-pipeline DLX implementation and see whether this gives us any insight into how to break up a DLX implementation into pipelines. This is what I showed before. These are the operations done for all instructions, and then there are 3 or 4 phases of operations done differently depending on each instruction. Well, one thing you might think of doing is taking all of this stuff, making it stage 1, all of the ALU stuff, making it stage 2, all of the memory stuff for stage 3, all of the register write-back stuff for stage 4, and all of the PC updating stuff for stage 5. Gives us a 5-stage pipeline. We can clearly define the demarcation points and put registers saving state information in between them and build our pipeline machine. Why might this not be the most ideal pipeline for DLX? Anybody have any guesses? Come on, somebody.
Well, for one thing, some of the PC calculation can be done earlier, like for example on the way right.
Which one?
If you go to the way right hand side,
Yeah.
that can be, there's empty pipeline stages where that can be filled in with.
Okay, that's one thing. You could consider moving these things up. But remember, you've got to be careful so that 2 instructions don't try to use the same resource at the same time. But yes, that's one reason why this isn't great. You can move some of these things earlier. And in fact, some of these things can be moved to a place where they overlap some of the other operations. There's no reason to wait for the PC to be updated with the next PC necessarily down at the bottom. Anything else besides that? What about the idea of trying to make the time it takes to do each stage relatively the same for all stages? Well, one of the things you notice in stage 1 here is that it's doing a memory reference to fetch the instruction register. Then it's doing memory references, registers after all are just memory, to fetch registers. So this is going to be a relatively long stage. You can't begin the register fetch until the instruction has been fetched out of memory. So this is going to be, in total, a relatively long stage compared, for example, to the next one, which is, after all, just doing an ALU operation. Now, maybe you didn't know that. I mean, that's making the assumption that ALUs are relatively fast compared to memories, or at least compared to 2 memories in serial. And in fact, that's true. In order to make this kind of decision about what things ought to be in what pipeline stages, you've got to know approximately how long things are going to take. And in fact, you'll see different variations of pipelines for the same architecture that move things from one pipeline stage to another as the implementation used for the functional units in any stage changes. If you can somehow figure out a way to make this memory and the register memory blazingly fast compared to an ALU, then it might make sense to put all this stuff in one stage. But in fact, they're not. And a better division would be to do something like this, to have a stage which fetches the instruction out of instruction memory. You can be incrementing the PC, because notice that these 2 things can happen at the same time. And the next stage should be the one that fetches registers out of register memory. And that makes these 2 stages roughly the same time. And it makes those 2 stages more comparable to how long it takes to do an ALU operation. Next time we'll go over the staging for DLX in detail and see how it gets pipelined. Programming assignments due next time.